Good afternoon, everybody. We are Nicolas Guire from OpenTech and Imanol Allende from Codethink. And we are going to present safety and safety techniques to a statistical world. So let's start with the context and motivation of this presentation. We know that the next generation safety-related systems that we are trying to build today includes technologies that include deep learning or AI. Also, security plays a key role, and they have high-performance computing architecture, right? We want to use this high-performance computing architecture. However, there are some limitations compared with the traditional techniques that we have. The industry aspires to employ commercial off-the-shelf multi-core processors for these critical applications, but we need to take into account that this hardware was designed for maximum average performance and not predictability. Currently, there is no certified high-performance multi-core hardware available for safety-related systems. There is some hardware, but they have lots of requirements for the software, so when you try to use it for your use cases, it's not possible to use it. So there is a misalignment with the traditional safety standard also for these next-generation safety-related systems. Functionally, safety standards were originally designed for simple and more deterministic hardware in mind. So they were specifically targeting single-core, real-time deterministic systems. And the safety techniques or measures that these standards propose were thinking in those type of systems. It is essential to note here that we are not saying that these techniques are not good. These techniques have been proven to be effective for this type of systems. But we are trying to build a totally different world, right, with the next generation safety-related systems. So we see that there are some challenges applying these traditional techniques. The critical systems that we seek to certify are inherently complex and non-deterministic. They often involve concurrent execution, they have shared resources, and there is a variability in their timing behavior. As a result, some of the existing safety measures and assurance techniques that the standard propose are not enough, and they fail to provide the necessary confidence. Some of them, not all of them, but some of them, they are not enough. So to address these challenges, we must explore and adopt new safety assurance techniques that take into account the features of the system we are trying to build. We need to have first, we need to identify this feature and see which are these systems, and after, propose new safety techniques for that. It is very important also to notify here that safety standards are not prescriptive. They are open to new alternatives. The only thing that we need for this alternative is progress explanation, justification, and evidence to show the safety claims that we are doing for them. Also, something that I have heard during this conference and many of them, we try to focus in testing for the safety, but the safety standards are about testing and analysis. And analysis is also very important to get it. And we shouldn't forget about that, the analysis part. So what we propose in this presentation and what we have been working during the last years is to embrace statistical techniques. So this already happened in different scientific domains. The statistics have used for these scientific domains instead of deterministic models when they were dealing with uncertainty and randomness. So one of the examples is the biological domain. They used a lot of statistical models when they need to try to understand or get numbers from something. And also the statistics in safety, it's nothing new. There was always there. If you check part 2 of 6158, you can see a statistic for hardware. So it's not a new proposal, it's not a new idea that we came with that. I also want to explain how we get to this. So when I started checking these complex safety-related systems, I found that there was lots of teams. One I really like it was Carles from University Polytechnic of Valencia, that they were dealing with probabilistic worst case execution time. They were proposing to do probabilistic worst case execution time to calculate the worst case execution time. So they doing extreme value theorem, they can predict the upper bound execution time of the task and ensure that the safety task is going to meet the deadline of the critical system. So that's why I see this, and I thought this is a great idea to use it. Can we use these statistics in order to, for other measures? And that's how we started. So one of the cases that we have checked is to calculate the estimation of failure rates in software and the common cause failures. So in the systems that we are trying to deploy, achieving 100% test coverage, it's not reasonable achievable, and maybe it's not necessary neither. In non-deterministic system, it's hard to identify all possible execution traces because we deal with uncertainty. So we know, and if you check the literature, we know that the Linux kernel is non-deterministic. This means that for the same application with the same inputs, it may follow different execution paths. This is one of the examples. We saw, for instance, we have data showing that system call write, normally it's executed something like that for writing in def null, and after we can see RCU context switch in almost any point of the execution trace. This is done if you execute the application repeatedly, you will see that. It's easy to see. So traditionally, we have this single execution trace for one input, but now we have several execution traces that happen in the complex systems, and this is depending on the global state of the system. So a few points that are important in non-determinism. It is not possible to force the execution path, to force the specific execution path. It does not rely on the inputs only, it relies on the global state of the system, and this state is not generally reproducible because it's too complex. So it's not possible to achieve 100% test coverage. So when we wanted to do this estimation of failure rate, we started collecting data. For that, we use F-trace tool. F-trace tool, it's widely used by Linux kernel developers. It's built in the Linux kernel. It's highly configurable. It's highly tested. And basically, we have our critical task executing, and we were recording what's happening there. After we did some post-processing of these traces to clean them and calculate hash values. So with these hash values, we can see if the trace has happened several times or a few times, the frequency of execution, when it has happened. It's easy to analyze after with statistics. And we get plots like this. So for the critical task, we saw that the majority of the times, we have the same execution traces being executed. These normally are the shortest one, and this makes sense because Linux has been developed with performance in mind. So you want a sorted trace to be executed. But there are cases where there are very weird traces that are being executed. And if you see the plot in the right bottom part, we have a lot of traces that has happened only once or twice. So if we have traces that has happened only once or twice, we cannot say that there are traces that we have already tested. There will be unknown traces there. And those are the dangerous ones, the ones that are not tested. The tested one, we know that it works, and we are safe then. So we propose it here to do a statistical path coverage. So we have the data that we collected first, and now we can model it. For modeling, I'm not going to go in detail, but we use a power law model. It's widely used when you are dealing with frequencies and heavy tails, and we model with that. And after, we wanted to calculate the risk. Risk is probability multiplied by severity. So we need to calculate the probability of an untested trace being executed, right? For that, we check the methods that are available, and we identify simple good Turing. That simple good Turing is used to calculate the probability of an event that didn't happen. And it uses information of events that has happened once, event that has happened twice, whatever. So with this simple good Turing technique, we can know the cumulative probability of an untested trace is happening. And a conservative approach would be to calculate the risk to say, okay, any untested trace, it's severity 1, it's catastrophic, and therefore we have the risk. We can calculate the risk in software of our safety application, right? But we think that we can do better than that. We can capitalize on complexity. So we can capitalize non-determinism in this case. Non-determinism, something that seems that it's going to hurt us, that it's bad for safety, can be useful for safety. We can use this non-determinism to improve the safety using a redundant architecture. That means executing the same application in 2 times, 2 or more times. So known traces are safe because we have tested them and we know how they behave and that they behave correctly. But untested traces are the dangerous ones, right? And we don't know which traces can be executed. So here it's, which is the question that arises is, which is the probability of 2 untested traces happening at the same time? And these choose consistence, and these 2 consisting in a common cause failure, right? It's not the same 2 untested traces that doesn't share a common cause failure or 2 untested traces that they have a common cause failure. So for that, we calculated the beta factor, that is the fraction of untested traces, and we used correlation of execution sequences. This is a conservative approach because we consider that all of ray traces have a common cause failure. So we get a very conservative approach from the safety perspective. And therefore, we can calculate the probability of dangerous failure. That's it. We multiply beta factor that we have estimated, probability of channel A of executing an untested traces, and untested trace, and probability of channel B of executing an untested trace. And now, Nico is going to explain you the statistical residual bug detection.
Okay. So that was sort of the complex part of using statistics, where we are trying to replace a deterministic method by a statistical method. One of the things that we have in open source, it's a problem that we don't have that much process information, or the process is not compliant with 61508. I'm not going to address any of the domain standards because the domain standards cannot be used for complex systems. If you want to reference at 61508 part 1 4.2 that explicitly says domain standards are only for low complexity systems. For anybody that tells you that he's using 26262 for the Linux kernel, please tell them to read 61508 and forget that nonsense. So we have to get a handle on the process. We normally cannot go to the kernel developer and say, well, tell us everything you did and we'll assess the correctness. But we can do an indirect assessment of the process by looking at statistical properties. I'll show you a few of the simple ones to start with. First one. So the first one, or the 3 that I will be introducing is the bug lifetime that we have in the Linux kernel. You might wonder why we're only talking about the Linux kernel, because that's really the most complex and most non-deterministic element in the system. Other elements are runtime deterministic or moderately non-deterministic, so they're easier to handle. So we'll look at bug lifetime, then using machine learning for classifying commits as bugs or non-bugs, which is interesting because 61508 table A2 explicitly says AI is not suitable for critical systems, not even for diagnostics. But if you look at it in part 7, what the argument for that is the lack of assurance for machine learning. So we have to address that. I'll show you how we think we're doing that. And finally, we'll look at a very simple trending model to actually estimate the residual bugs that are still in a particular Linux kernel. And basically what we're saying is we don't know the process. The process stays a black box to a certain extent, but we look at the output of the process. And then we can say, is the output equivalent to what we would have gotten if we had done a bespoke process, a 1S process in 61508 context for the Linux kernel? And the answer, I think, is yes. Next one. So, very simple case is looking at the bug lifetime. How do we do that? Basically, the Linux kernel developers in the 2.6 kernel started introducing the fixes tag. Basically, when you fix a bug, you put a fixes tag into the commit message that points to the original buggy commit. It took quite some time for the uptake of that, so maybe beginning with the 4.x kernel, fixes tags were relatively soundly established. But currently we have about 27,000 fixes tags up to the 4x kernels, and the latest kernel is something like 75,000 fixes tags. So we have a fairly good population of bugs that we are very sure that they are bugs. So we can take that and we can then just look at the lifetime. How long did it take from introducing the bug until it was fixed? If you look at that curve, you can see that the average bug lifetime is a little bit less than a year, or the mean of bug lifetime is a little bit less than a year. And if you would take a kernel that is, in this case, this is for a 6.6 kernel, I think, I'm not quite sure, about 320 days, and you would take a 320-day old kernel, then you already eliminated about 75% of the bugs. So just by selecting, you can eliminate a lot of the problems. I know that this is not hugely popular to take an old kernel, but we're not talking about a really old kernel here. And if we look at a project like CIP, they are maintaining a very long-term stable kernel. They're, in this sense, very old. Unfortunately, they're not that stable at the moment, but that's a different story. So we can use this. How can we apply this to an actual configuration? Because this data is for the entire kernel. Well, then we have to filter out the specific set of commits that is in our kernel. How do we do that? We take GCC's ability to emit lines during line information during compilation. Then we take this line information, change it back to the SHAs of the commits. We have a simple tool called line to SHA and the patch impact tester to run this machinery. And then we have the list of commits that are in a specific configuration, and then we can calculate how many bugs do we expect to have in that based on this first metric, age of the commits. So you can boil down the residual bugs quite nicely with this fairly simple trick. This is just one of the many methods. Don't take this as anything like a silver bullet or so. The next one. So the next one that's maybe a little bit more interesting is looking at how we can use machine learning, because as Dirk Honel during his keynote made clear, you can't give a presentation without using AI or machine learning at least once. But it actually is a fun thing to do because it is dirty data. And statistics is not very happy with dirty data. But machine learning is dirty, so it loves dirty data. And that's what we did. Basically, so we take supervised learning model, and what do you need for a supervised learning model? You need labeled input data. Now, the fixes tags we already covered. The fixes tags is easy. The non-bug commits are a little bit of a problem, because if you just take everything that has no fixes tags, you have a lot of bugs. Now, we can eliminate some, as we saw, just by looking at the time and saying, okay, I'm not going to take any of the more recent commits. I take commits that survived the kernel for, let's say, 2 years, then already eliminated 80% or a little bit more than 80% of the bugs. And there's some other methods. We'll see one then later when we look at trending. So we can get relatively good data on that. Then we have to, of course, look at the features that we're going to use, that we're actually going to train the model on. The idea that we don't need feature engineering and machine learning is also one of these myths that I hope people don't really believe. We do need feature engineering, otherwise it's a classical shit in, shit out situation. So you need to look at plausibility, and safety is about taking a plausible hypothesis, designing your data, putting your data into model and verifying it or falsifying it. Just looking at a correlation and say, oh, this looks interesting, and then afterwards coming up with a plausible explanation why this might be reasonable, that's not going to deliver safety, and it's going to cause problems when you have to update. So we engineer these features. Some of them are trivial, like lines added, lines removed. That's a no-brainer. Then other things, how many CC'd byte tags are there? what is the complexity of the directories that are being modified, how many files are being used, things like that. Some of them have to be pre-processed, like as I noted, directory complexity. Is this a tree-wide update, or is this a single file that's being updated? It's a big difference if I'm changing 700 lines of code, but I'm changing it in 350 files because I'm just updating kmalloc memset to kzalloc as a concrete example. That's a tree-wide update. It's a simple update, so the complexity is not in the lines of code. So we have to look at these features. We can model that. Then we get it's not really a probability that we get out of a prediction from the inference process of a machine learning model, but it's roughly a probability. And then we can put a threshold onto that probability and therefore extract highly probable bugs, buggy commits, or less probable, or apply it to the entire kernel. Next one, please. So how are we generating the assurance? Because that's the key thing that we need to solve for safety. We want to use machine learning for safety. This is only at the tools level. Don't try and do anything like this for an actual online machine learning model. That's a different can of worms. If anybody's interested in that, we can give you our views on that another time. So we have a supervised learning model, as I described. It's a very simple model, keeping it simple, fully connected stacked network. Actually, it's just 3 or 4 layers, relatively simple. That makes it understandable. You can easily generate heat maps and things like that to understand what's actually going on inside the model. Already covered how we're getting our fixes tags and or bugs and non-bug commits, and then we can bootstrap on different concepts of how we get the non-bug commits to make sure that we are actually seeing what we want to see. And then we can use simple XAI, explainable AI tools like SHAP in this case. You can think of it a little bit like a principal component analysis that you would use before you do a regression analysis. You have these, I don't know, you have your 100 parameters and you want to know which ones are really important for your regression analysis. You do a normal PCA on that. And SHAP is something similar. It will extract which of the input features had the greatest impact on your model outcome. Then, of course, we have the luxury in open source that we have a lot of data. This luxury is generally not true for proprietary systems. So if I want to test my model, I just go back to the 4.4 kernel, extract those that have the highest bug probability according to our model, fast forward and say, how many of these patches are still in the 6.13 kernel? Or with what were they replaced? Sometimes it has a fixes tag, sometimes it doesn't, but you then can see that these were actually bug fixes very often. Sometimes of course, the code was just replaced. And then we can do the same thing by applying this as a general metric for the entire kernel and looking at trending there. So next one. So this to show you what SHAP looks like. I'm not into beautiful images, so apologies for that. But it's, as I said, it's basically a principal component analysis equivalent for simple machine learning. It's basically for each of the parameters, it's telling you how important is it and in which direction is it moving the decision, the verdict of the machine learning model, and then you can check if your hypothesis, your expectations are met or not. And that is how we can generate assurance for the models. Next one. So what does that look like? That's the one with the sublevels, right? Yeah. Okay. This is, I think it's a 6.6 kernel. The sublevels for each of the sublevels, the number of commits in the sublevels, and then we looked at for a certain threshold. I don't remember what it was, 0.7 or something like that. How many highly probable bugs do we have? And you see that it's actually quite consistent proportion of the actual commits that are in this kernel. Now, remember, stable sublevel is only fixes. So there's no new features in there. So we would be expecting that this is fairly constant over time. I would have hoped that it's a little bit less than this, but okay, that's the way it is. But this is a way how we can develop selection criteria for kernels. Which kernel am I going to put? into the system, which am I not, and we'll then maybe be able to show you what a stable and unstable system looks like. Same thing, trending over the 6.x kernel. Next one. Probably can have a discussion with some kernel developers on this, but if we look at mean and median, we can see that actually the average bug classification rate of the commits is going up, even though the total number of commits per major release is not really going up. It's fairly stable over time. I think yesterday was the number from Kate Stewart at 9 commits per hour, something like that, that we're seeing coming in at the moment. So it's fairly stable process, but we're seeing this growth of, at least with our model. Now, the probability that our model is wrong is, of course, not to be neglected in this case, but it's something we will be looking into if we can figure out why this is happening. Of course, growth in the core kernel is also quite high, from 4.4 to 6.12. The kernel, directory kernel with all the main kernel function grew by more than 50%, grew by more than 50%. So these are really significant growth, and these are highly complex code in these directories. So that's why it's relevant. Of course, a lot of this is drivers. We should probably filter out drivers, but if you're interested in the detailed statistics over all the subsystems, we can deliver those if you are interested. Okay, next one. So third method that I want to briefly introduce is very trivial trending. Not hard to see what we're doing here. It's just a nonlinear regression. Probably if you have a count model like this, this is sublevel commits for a stable LTS kernel. In this case, I think it's 6.6 again. We know these are only bug fixes, no feature increments. So CVS and just performance, significant performance problems or incorrect behavior issues in the kernel. So basically you would expect this to go down over time because you're removing bugs from the system. At some point in time, you hope that we go out of bugs in the Linux kernel. I don't think this ever happened, but yeah. So problem with using simple count models, I would point to a Poisson distribution, is that we have massive overdispersion in the Linux kernel because it's human processes. Had a massive outlier when LinuxCon was in December, and then there was Christmas and then New Year's. So we had some like 4.5 weeks of very, very few commits in the Linux kernel, and that made a mess of my statistics. So I had to switch to negative binomial distribution to compensate for the overdispersion. Result is that the numbers are a little bit less optimistic than they should be, and the confidence intervals grow, but that's okay, it's conservative. What are we doing? We model, we create the model on the initial, I think it's 102 data points, and then we extrapolate another 102 data points. Why can we do that? Because the timing of the sublevel releases is very regular. Everything in the Linux kernel is super regular. That means we can use very, very simple extrapolation strategies to then estimate what is the residual bug rate in the kernel. Might look quite horrific. You're saying, well, we still have some like 70 bugs estimate per sublevel cumulative. That's not that bad. If you do that over the next 3 years, you would say that's roughly equivalent to 1 bug per 3K lines of code. NASA said the best they think humans can do is 1 bug per 5K lines of code. That's what they estimate the Space Shuttle flight control system has. So I would say a little bit more work to do, but we can get close to flight control systems of NASA, and that's really the top notch that is possible. I would love to see a curve like this for other proprietary operating system. They're hiding them and they know why. Okay, next one. So, but we have one more thing to do, and that is, if we have nice measures and techniques, we can use, well, we need an argumentation for them. And this is really just a nutshell presentation, of course, we're not going into details. Would be a seminar for a full day, but we'll show you briefly what we're doing. First one. So when we replace a measure technique, a classical measure technique, as we saw before, code coverage, it could be instruction coverage, path coverage, whatever, we replace it by something else. We want to have a one-to-one replacement. But what does a one-to-one replacement in functional safety mean? Every measure and technique in functional safety has properties attached to it. If you want to see the details, 61508 edition 2 Annex C will give you all the detailed properties. They're defined or specified in detail in Annex D of Part 7 as well. So you get a property matrix. For every property or for every measure and techniques, it's contributing to a certain subset of the properties. Could be understandability, completeness of testing, freedom of interference, absence of common cause fault. These are the typical high-level properties that these measures and techniques are supporting. So we take the matrix entry or the Annex C entry, I'm treating it as a property matrix. Basically, y-axis is my measures and techniques catalog, x-axis is my properties, and then just treat it as a matrix. And you're trying to populate this matrix with a reasonable set of measures and techniques to achieve completeness. So if we take path coverage or something like that out, then we say, okay, we're weakening these 3 or 4 properties, and then either we can replace it by one measure and technique to replace these properties, or we need to do more of them. But essentially, it's a one-to-one replacement. You don't want to actually just throw a new property in. Why? Because these traditional measures and techniques don't fit our technical systems, but the objectives of the traditional system absolutely stay the same for our new systems. And that means at the property or tool level, the properties that we want to achieve stay the same as well. Arguing away and say, oh, we're not going to have code coverage and we just don't care because we're doing testing, we don't do analysis, that's of course nonsense and trying to cut corners. If anybody wants to see what happens when you do that, then go a bit back into history. US Air Force in 1948, without having a military conflict on this planet, lost 7,200 aircraft in 1 year. Seriously, 7,200, that's 20 per day. Why? Because they were having super high assurance per component, but the airplane complexity was growing so much that even though every individual component had 99.99 something assurance, it was useless in these complex systems. And that's what we're doing when we're going for testing and say, oh, we'll test this component, and this component. Nice. You gained almost nothing in complex systems. I'm not saying don't do it, but you have to still treat the system level. So I'm not got ahead of myself because I actually think I covered the next slide as well. Okay, so the graph. What does this machinery of actually replacing one measure and technique by another one look like? I took a very simple one. One of them, requirements in 61508 for classical low complexity software is limited use of pointers. Kind of sounds like a joke in the Linux kernel to suggest that. So how do you resolve that? You go into the part 3 and say, where is it being requested in detailed design? What is the specification? Go into part 7. What is the aim? What is the description of these methods? What are the dependencies on other methods? Go down into there, say, we are going to replace it because we look into Annex C, we know the properties it's trying to achieve. The property argument for limited use of pointers, main argument was improved testability. Well, that might have been true in 1990, that pointers were a problem for testing. Are they a problem for testing now? Not really. So you basically go through the argument, you reverse engineer the safety standards, because safety standards mandate transparency for your projects, but they're totally non-transparent themselves. So you have to actually reverse engineer safety standards to find out why did they call for this measure and technique. And then you replace it by, in this case, reasonable, or I don't remember what I call it, well-defined use of pointers, I think it is. And you plug that in, you give it the same properties if you can justify that, or maybe you need to add a second measure or technique, like some static code analysis tools to cover some corner cases, Codethink scripts, battery of Codethink scripts to handle certain things. And then you say, okay, we achieved the same goal. And that's really what we're trying to do when we use 61508, which is the only suitable standard for complex safety-related systems. It's super flexible. This is in line with 61508. Don't try and do this with ISO 26262. You will be shot on the spot by the first safety assessor. That's why they don't carry weapons. So you need this flexibility in this transitional technology, and 61508 is the standard that gives you this flexibility. Okay, I know this is a little bit brutal because we're not really explaining the details. It's just the carrots. We want to show you there are statistics. Statistics can solve a lot of problems. There is a lot of formalism that you have to satisfy so that you can justify it. But at the end of the day, safety is just about answering a single question. Why did you do X? And as long as you can answer that question, you're fine. Thank you. Okay. Questions?
When we talk about is versus ought, this is a presentation about how things are. Do you think your model has enough signals to tell us if the Linux kernel development process ought to be different in some way?
Can you go to the good case and to the bad case? I'll show you a good case and that will answer the question, I think. The good statistic and the bad statistic.
That's a stable.
Okay, that's what a stable kernel, I think it's a 6.6 kernel, full kernel, kernel subdirectory and subdirectory. You can immediately see that it's stabilizing. So that tells us the Linux kernel process does look reasonable. I don't think we need to fix anything. Yes?
Well, you were looking at meta information. You had a good slide on meta information on a patch. That seems like some ought information may, given your data, is there anything we could do at that stage, at the patch review stage and all that, that would lower the bar there?
The goal of this tool is to say, how can we focus the limited available effort or resources of maintainers so that you review the patches with the highest probability of discovering a bug. It's not to say we want to, I mean, of course we could take a metric and say, if the commit message is longer, the bug probability is higher. Sounds maybe counterintuitive, but it makes a lot of sense because the higher the complexity is, the longer the commit messages get. But I'm not saying please increase the length of your commit messages as our statistics goes down. That doesn't make sense. So it's really a tool to allow you to focus on commit messages, which ones to review. You want to know what's going wrong in the Linux kernel. There are other ways to analyze that because we didn't cover those today.
Cool, thank you.
Maybe we should show them a bad kernel too. That's 515 kernel. Oh my. Ouch, right? You don't need to really know anything about what a negative binomial distribution is to know that this doesn't look very good. And especially it's not just the full kernel, it's kernel subdirectory and subdirectory. And if kernel and are screwed up, yeah, you're asking for problems.
Okay. Nicholas,
yeah.
Thanks for the good presentation. I have one question. It seems that your assumption is that just a bug per se is dangerous. But as a frugal safety person, I would assume that a number of bugs kind of lead in the effect to crashes. So they're a nuisance, but they wouldn't keep me awake. Or the ones that would keep me awake are the ones that lead, for example, to silent data corruption. Have you done any work on classifying the bugs in the statistics to weed out the ones that, from a safety perspective, are kind of more concerning than the less concerning self-evident ones?
We tried doing that, and we had a very pleasant result, unfortunately statistically unpleasant result. I took 30 bugs randomly. I sent the kernel developer that wrote these bugs an email with my analysis of the bug, that it was a design fault, that it was a coding fault or whatever, and asked them to confirm. Then I sent the same email to the person that submitted the fix and asked them of their opinion as well. Return rate was more than 80%, so any sociologist would be jealous of that. And the conclusion was that from the 30 bugs analyzed, not a single one was safety related in the sense that you're talking about.
Okay.
We had a whole bunch of crash stuff, but crashing systems is generally okay.
Yep.
If they just stop operating,
Yep.
we need other defenses anyway. We haven't had a safety critical, we weren't able to pinpoint a safety critical bug for our use case. That's of course not saying there are not, but actually, if we just look at how few of the kernel bugs are currently deterministically reproducible in the stable or the LTS kernel, you will hardly ever find a bug report saying, if I make this call, bang, the kernel is dead. So you get these emails of, if you run this overnight under very high load conditions on an x86 where you set number of CPUs equals to 3, then you maybe will trigger. And that's what's really protecting us. So to answer your question more precisely, at the moment we're doing the conservative assumption, everything that's untested, every bug is catastrophic, simply because putting a severity on them requires a use case to be in context. And unfortunately, industry does not yet like the idea of doing certification in context. As soon as we can do it in context, we could really consider that and appropriately reduce the severity.
Okay, thank you.
Thank you for the presentation. I have two questions. One is you have written or you are writing a paper on these matters. And the other question is if you can elaborate a little bit why ISO 26262 is unsuitable for the kind of systems you are targeting here.
Okay, I'll start with the second question because I like that one. Very simple answer. 26262, if you look at it from the development, it was based on traditional human-operated cars. I know in addition to it, they tried to do a few tricks to get into the autonomous sphere, and I'm not going to comment on SOTIF. But the main problem is 26262 has a normative reference to 6215 So if you're reading 26262, you should actually be reading 6158 before you continue. And you would have done that when you read part 1 definitions. You come across normative references. You go into 6158 part 1, you stumble across clause 4.2, and 4.2 says, if you're in a high complexity system, use this standard. If it's low complexity, you can remove some of the requirements, or if there is a domain standard for low complexity that has accumulated adequate knowledge of the domain, use the domain standard. For everything else, use 6158 directly. Unfortunately, the people buy ISO 26262 because it has automotive in the title and think that's what to use. It's not. This is true for rail industry, for machine tool industry, for everything else. That's why all of the standards, ISO 26262 edition 1, clause 12, said if you want to use a different industrial standard, note, possibly 62158, then this is compliant with ISO 26262. Now it's in edition 2, it's in part 8, clause 16.2 or so, where it says you can reference other industrial standards, including 62158. So all of these standards have this backdoor. You go to process industry 61511, it explicitly says complex systems back to 61508, low complexity stay in 61511. we removed all the complexity of process industry. 62061 does the same for machine tool, and so on. The only ones that didn't get it were the automotive people. They just, I don't know why that happened. I'm really confused about that. But the thing is, if you use 26262, it's not a very flexible standard. So you're going to break your fingers trying to argue Linux in 26262 context. Why would you want to do that? 6158 is a straightforward path. It's not nothing to do. It's a lot to do, but it is straightforward. It's super flexible. It's normatively compliant with 26262. Why do you want to do it so painful?
What about the paper?
I was trying to get out of this, but well, I'm lazy and writing papers, but we did document a lot of the CO2 Linux project. These documents are available at OSADL. And we are writing papers from time to time. We do that. But if you have specific questions, I would be very interested in these questions. And I don't mind, I'm an open source developer as well. I don't mind spending time answering reasonable questions with lengthy emails. I'll be happy to do that.
Thank you.
Put them into papers from time to time.
Hello, thank you for your presentation. I have a quick question. You were talking about the industrial and automotive market. Did you have a chance to engage with the avionics market, in particular EASA and FAA, in the initiative they started several years ago of defining overarching approaches in order to sneak in new approaches, like for example, not use the ones on THC?
So I know that there's a lot of standards popping up all over the place. I mean, we have UL 460, standards, we have the machine learning standards, we have edition 3 of 6158 upcoming. I don't really know how to engage with the standard community. If you have a good pointer how we could get involved in that, I would be very happy to do so. Currently, I think you can't afford doing it. If you want to work on the 6158 committee for edition 3, you have to pay €70 for every of the intermediate copies. I'm a small company, it would be 25% of my turnaround this device, and so I can't do that. If you have a avenue to contribute to new methods, develop methods, except at that academic level, I'm very happy to hear about it.
So we can talk about it, because they are open to anyone to do that. You just need to have an applicant. So you don't have to go through a definition committee. You can go directly to them with someone that would like to use your method, for example.
Okay, so we developed a lot of alternative methods in context of CO2 Linux. They're all open source. Don't shoot us for the ugly code. We didn't have the time, resource, really clean them up. My code especially is classified as ugly. But I got 300 patches except on the Linux kernel, so it can't be that bad. But yeah, I would be happy to discuss measures and techniques. And as I said, we did document a lot from CO2 Linux. Those documents are available. There's also a lot of interesting work going on in some other companies that are looking at certification. We heard about some of them. I'm associated with Codethink. I think they have an interesting approach. Well, there's still some work to do. Okay,
Thank you.
okay, thank you.